Well, we are continuing our thrilling journey through series to talk about alternating series. So alternating series, as you saw in the book, are just series that alternate, that's the name, between a positive and a negative. So there are kind of two really big concepts in this section. There's the alternating series test, which is going to tell us if an alternating series converges or not. And then there's this idea of conditional convergence and absolute convergence. Okay, so there are three things. So let's talk about first the alternating series test and do some examples there. Whoa, settle down there, whiteboard. And then when we go to do, conditional and absolute convergence, we'll see that the alternating series test will sometimes come up. Actually, it could come up quite a bit. If it's not absolutely convergent, then if it is conditional convergence, then we use the alternating series test. So this guy right here, again, I'm being a little bit lazy here just because I want to be, it doesn't have to be k plus 1. It could be just k or whatever. This guy converges if the following are satisfied. Right, so there are two things you have to show when you're doing the alternating series test. The first thing you have to show, this is going to be a really bad way of putting this, but eventually, right, we have to have that a plus k is less than or equal to a sub k. A sub k plus 1, excuse me, is less than or equal to a sub k. So basically what that says is that the series is non-increasing in magnitude, and this one right here, you have to show. This one right here is going to be one that's going to be tricky to show. And then the next one is the limit as k approaches infinity of the kth term must be 0. So when you're going to prove if an alternating series converges or not, if you see, that number 2 is not satisfied, you can jump to that right away, and then you'll be able to say for certain that it doesn't converge. If you see that number 2 is satisfied, of course that's important, right? But then you also need to make sure you're showing number 1 and number 2. You need to show both of them. So let's do a couple examples. A note right here that they show the alternating harmonic series. This is one now that you're going to need to know just from looking at it. So just like we know that the harmonic series diverges, now you should understand that the alternating harmonic series, which is this guy, it actually converges. And I hope you will take the time to look in your book at the proof of this. This converges. Now, how do we know that? Well, remember, it has to satisfy these two properties, right? So is a sub k plus 1 less than or equal to a sub k? Well, if I take the, and I think I need, yeah, and we just, the a sub k here in this case, right, because we have a negative 1 to the k times 1 over k, this is my a sub k. Just trying to be consistent with what your book says. So is 1 over k plus 1, right, that would be the kth plus 1 term, is that smaller than the term before it? And it is, right? And how do we know that? Because we know that increasing the denominator makes the number smaller, right? So if I increase this number right here by 1, then I know that that resulting number is going to be smaller. Okay, so you don't have to prove that. If you're just increasing the denominator, you can automatically say that this inequality is true. However, if there's stuff in the numerator, you can't just say that's true. We don't know that for sure. So I'm going to show you some examples of what we can do to show that it is non-increasing, or another way to kind of say that is basically to show that it is decreasing. Okay, and so we'll do that. I'll do one for you here. In a minute, that we have to actually, what we're going to actually use is we're going to use the your derivative, don't you? I miss the derivative, don't you? I do too. So really quick, let's just look at determine everything. Determine if the alternating series, I'm kind of running in here, that's okay, alternating series converges. So, for example, if I had something like this, negative 1 to the k plus 1 of 2k all over k minus 1, let's say. Let's do k plus 1. Okay, so I have negative 1. This is an alternating series, right? Because I go from positive to negative, and my a sub k then is this 2k over k plus 1. And so remember the two things I have to show. I have to show that that gets smaller, right? And I have to show that the limit, for it to converge, both of these things have to be true. So number one's going to be hard to do because if I replace this k with a k plus 1, it's not totally obvious if this guy's decreasing. So I mean, I'm trying to get a feel for, is this going to be convergent or not? And as I look at this a sub k, think about what happens as k goes to infinity. Notice I have the same degree k on top as I have on bottom. So I know that when I take the limit, it's really just going to be the ratio of the coefficients of those terms right there. So it looks to me like the limit of this isn't going to be 0. So I'm going to go ahead and take the limit. I'm going to go with number 2 first, because why put in all that work in number 1 if number 2 is going to fail, right? And so I'm going to take the limit of this. Sure enough, it's 2. That is not equal to 0 last time I checked. So what do I know about this alternating series? It does not converge, it diverges. And you're done. Wow. That's an amazing pentagon, right? Look at that. What about something like this? So k equals 1. I want to grab you one that is a little bit more interesting than that. But what about something like this? K equals 1 to infinity of 10n all over, oh, I keep using n's. I think I even put n's on your fun sheet, sorry. Maybe not. 10k all over k squared plus 16. So as I look at this, I can kind of see that its limit's going to be 0, right? As k goes to infinity, the denominator has a higher degree than the numerator, so the denominator is going to grow a lot faster. So this sucker is going to go to 0, so that's good news, right? So it's going to satisfy 2. But let's start with 1 here, and what I need to show is I need to show that the kth plus 1 term is less than or equal to the kth term. That's going to be a problem because if I just replace this k right here and this k right here with k plus 1, that's not obvious that that is going to be less than a sub k. Now, if this had just been 10 over k squared plus 16, then I would be able to say that this is true without having to really justify myself, right? Because if you notice, if that k wasn't in the numerator, then I would have had just a straight, I've just increased the denominator. I know if I just increase the denominator, it makes it a smaller number, so we would be done. But of course, that's not what I gave you. And so let's see what happens with this one. So the trick we're going to use, and you had seen this in your book, is that I'm actually going to consider the function f of x equals 10x over x squared plus 16. And what would it mean for this function to be non-increasing? Well, it basically means that this function is decreasing, right? So remember, if I have this function, whatever it does, the values of my series are just going to be, each term of my series would just be discrete points on this function. So if I can show that this function is decreasing, then that basically, it follows, right, that the terms of my series is decreasing also, because we're just taking specific points on the graph of that function. Well, how do we show that a function is decreasing? That's right. What was your answer in Calc 1 for everything? Take the derivative. So that's going to be our answer here. It's kind of nice to come back to it. So let's take the derivative of this. So I'm going to do a little bit of quotient rule. A little bit of quotient rule is always a good time. So I'm going to do, this is my saying down, I know, d up, minus up, d down, whoops, minus up, d down, all over down, down. Or I know most of you probably learned low d high minus high d low or something like that. I learned down d up minus up d down from like the greatest grad school teacher ever. So if I simplify the top here, looks like I get 10x squared plus 160 minus 20x squared, right? All over x squared plus 16x, or plus 16 quantity squared. So let's just, what I want to just consider is the numerator. And the reason I want to just consider the numerator is because the denominator is always positive. And what I want to show, if I want to show that this function is decreasing, then I need to show that its derivative is negative, right? That's what a derivative is. So when is this derivative less than 0? That's what I'm going to take the numerator, simplified it a little bit, and I'm going to figure out when it's less than 0. Subtract the 160, so I get negative 10x squared is less than a negative 160. Divide by negative 10. Remember here, people, Come on, people. Remember here that when you divide by a negative, you switch the, you remember that, right? You remember it, yes. You switch the, that thing. What is that? Oh my gosh, the inequality. I haven't had enough coffee today, you guys. So, now, you know, when is x squared greater than 16? Well, if I'm greater than 4 or less than negative 4, but I'm not going to worry about the negatives because really what I just care about is I only really care about positive values. So as long as x is greater than 4, this implies that we're decreasing, right? So is this going to work? Is it going to satisfy that first condition of the alternating series test? It is. I know I start at k equals 1, right? But eventually it starts decreasing. It'll start decreasing at k after k equals 4. So at k equals 5, k equals 6. Remember, this is an infinite series. So I'm all right if the first 4 terms aren't decreasing, as long as it eventually starts decreasing. So this is decreasing. So then that implies, right, that a sub k plus 1 is less than a sub k. And so number 1 is done. Right, so I've shown that that function is decreasing. Number 2 I have to show is true. That's pretty easy to show. I'm just going to take the limit as k goes to infinity of 10x all over x squared plus 16. Because, no, I don't want x's anymore. Come on, people. This isn't your fault. This is my fault. When I teach face-to-face, I blame. I have a class to keep me on track here. Here I only have my cat. She's not very helpful, or my 2-year-old. He's not helpful at all. The denominator gets bigger than the numerator, so that goes to 0. That checks. So what do I know about this series? It converges. Okay, and so that is how we do the alternating series test. All right, let's move to absolute convergence and conditional convergence, because when I do some examples with those, you are going to see that we're going to see the alternating series test. So my examples here, you've written this down. You should be writing down the theorems in your book about absolute and conditional convergence. Okay, so the instructions for this, sorry I'm saying so much today. Let's determine if the following series converge absolutely right? Absolutely. Converge conditionally or diverge. Now remember, absolute convergence is the same as convergence, right? So not the same as, but basically what this is saying is if I have a series that has some alternating in it and I take the absolute value of all of it, and instead of having those negative terms, everything's going to be positive, if it still will converge, if I make all those negatives positive, that's what we say absolute convergence is. It's a pretty strong thing. Yes, that series converges, right? We just say it converges absolutely to indicate that. It doesn't even need to take away some of those terms to make it converge. It would converge even on its own without it. So let's look at a couple of examples. So a really simple example, that is one that hopefully we can see pretty easily, but is one like this. If I add -1 to the, oh my goodness, why can't there just be a person out there that tells all the calculus book writers that they need to just use k or n? Let's all decide on it, people. My vote is for n, but we're using k. Okay, so let's look at this series. So I want to know, does it converge absolutely, meaning if I took away the negatives, will it still converge? If that doesn't work, does it converge conditionally, meaning if I left those negatives in, will it satisfy the alternating series test and then converge? Or if it doesn't satisfy either one of those, does it diverge? So if I look at something like this, what I want to consider first is I want to look at, I want to test absolute convergence. And I want to see this. You need to show the test, even if you look at it and you say, oh, I know this is going to be a conditional convergent one, which I hope you can get to that point. I don't care. You need to prove to me, I mean, I care. You need to prove to me that it doesn't absolutely converge. So absolute convergence, let's test that. So what is the series that I'm going to test for absolute convergence? Well, basically, I'm just getting rid of that -1 right there. Okay, and so I'm going to just, if I make every single term positive, that's just 1 over k to the 4th. Now I use all the methods that I've learned thus far in the chapter to determine if this is going to converge or not. Well, it is, right? This is a p-series. You don't have to do too much work with this. With p equal to 4, which is greater than 1, and it converges. So what do I know then? What is my answer then for this series right here? This series right here converges absolutely. Meaning I don't even need that negative one. I mean, it's there obviously because that's what the series is, but I wouldn't have to have it for it to converge. So I say it converges absolutely, it converges. That's exactly the same thing, but it's also kind of saying a little bit more of a strong point that I don't have to take away every other term, right? Every other negative for it to converge. Whereas if I had something like this, so let's look at this example, k equals 1 to infinity. Let's look at negative 1 to the k plus 1, it doesn't really matter, all over the cube root of k. Yeah, let's look at the cube root of k, that'll work. All right, so let's test absolute convergence, or if you're cool, ABS-CON. Yeah, I know. I don't know. I'm not cool. I pretend to be. I'm going to rewrite this as k to the 1/3 because I know this is a p-series of some sort, right? So absolute, if I take the absolute value, that means that negative 1 to the k plus 1 is gone. I get 1 over k to the 1/3. This is a p-series with p equal to 1/3, which is less than 1, so it diverges. So what do I know about my series up here? It is not absolutely convergent. You need to show me that. Okay, so right here I know not absolutely convergent. Okay, so now what is the next thing I'm going to test for? I'm going to test for conditional convergence. And conditional convergence is just basically, does this guy converge as an alternating series? Meaning, does it still converge even though I have that negative 1? So for conditional convergence, wow, don't know why that happened. I do, I accidentally tapped in my hand. I'm actually just going to look at the series itself, okay, and I'm going to do the alternating series test. So I come back to the alternating series test. Conditional convergence is also convergence. Both of these, you guys, are convergence. It just tells us a little bit more about this function. So conditional convergence says, yes, this series does converge, but it will only converge if we have that negative 1, if it's an alternating series. It would not converge if I didn't have that negative 1 in there, okay? So what are the two conditions again? I need to show that a sub k plus 1 is less than or equal to a sub k, and I need to show that the limit, I think it is going to converge conditionally, that the limit of the kth term is 0, or not the kth term, but a sub k. All right, so what do we have here? So my a sub k, right, is 1 over the cube root of k. So for number 1 here, I can just state, what would the kth plus 1, a sub k plus 1 be? It'd be the 1 over the cube root of k plus 1, which that must be less than 1 over the cube root of k, because that number, it must be smaller, right? The denominator is bigger here than it is here, and so it must be smaller. So we're good to go there. It's non-increasing. And then I didn't even have to do the derivative because I only increased the denominator, right? Not true if you increase the numerator, you have to do the derivative there. And then clearly the limit here as k approaches infinity of 1 over the cube root of k is 0. That satisfies it. And so this guy converges conditionally. It doesn't mean it doesn't. It converges. I don't want you to get mixed up with you know, these words. Don't get mixed up with words. I still could even just say it converges, right? But the question asks you to be more specific, basically. So the question, instead of asking just, does it converge or diverge, what type of convergence does it have if it does converge, right? And this is only with alternating series that we put these, you know, well, we could put absolute on any of them, but I hope that kind of makes sense. What about, let's do one more example and then we'll call this good. Yeah, I'm at 20 minutes almost already, so imagine you're getting a little over it. I can understand that. All right, so what if we had something like this? K equals 1 to infinity of maybe a negative 2 to the k all over, sorry, I'm having to think about this a little bit, and I don't like to think about it. Okay, actually, I changed my mind a little bit. Sorry. Okay, so what I actually would like to do is let's look at something like this. Cosine of k all over 4 to the k, I like this one, plus, let's say, 3 to the k. Okay, okay. So why am I talking about absolute and conditional convergence with this when it doesn't look like it's an alternating series? Well, it is an alternating series, even though it doesn't really look like it. The reason it is because cosine k, right, it basically bounces between negative 1 and 1. So this is technically an alternating series if we think of it that way. And so if I'm looking at taking the absolute value of this kth term here, right, I could actually say, so I'm testing for absolute convergence right now, plus 3 to the k, right? The absolute value of that, well, the denominator is always going to be positive, so this is 4 to the k plus 3 to the k, right? And then the absolute value of cosine, so what I'm going to do here is I'm actually going to do a comparison test. So what do I know? I know that cosine of x, the absolute value of it, this guy's always going to be less than 1, right? That's the biggest cosine can get. And then here, you can really take the 3k or the 4k, whichever one you would like, or 4 to the k. Let's take 4 to the k. This must be always less than 1 over 4 to the k. Because again, this I've increased the denominator, and 3 to the k is always positive. So I've increased the denominator, so this guy right here must be less than this guy right here, okay? So why did that help me? Well, this is the comparison test. What do I know about this series right here? 1 over 4 to the k. This is a geometric series, or a geo series, if you're cool, not really, where r is 1/4, and so the absolute value of that, which is just 1/4, is less than 1. So this converges. So remember, the comparison test tells us if I can show that I am less than a series that converges, then my series converges also. So thus, right, the absolute value of the cosine of k all over 4 to the k plus 3 to the k, that series, wow, that was a crazy sigma, converges. And therefore, what do I know, right? That's what I know from all this work up here. So what is my conclusion then for my series that I'm given right here? This converges absolutely. Okay. So when you're like, why is there a sign in this, right? They're really looking for you to compare it to 1, or they're looking for you to recognize that it actually is an alternating series because of that sine and cosine bump back and forth between negative 1 and 1. All right, guys, I hope that helps. This can be a little confusing, so make sure you look at the fun sheet. I have the fun sheet solutions. Look at them. Make sure you understand my notation. Notation is going to be really important, just like always, and let me know if you have any questions.